Hi everyone, hope you're doing absolutely awesome. One of Looser Technique's viewers asked in the comments to one of his videos whether he recommends titanium quick release skewers, and Raul replied that no, he does not recommend titanium skewers. He believes that titanium is too stretchy of a material for such use. Today I want to discuss why I believe that titanium is actually a suitable material for skewer use. Now let's compare some properties of the two materials. So in this chart which I prepared, on the left is iron alloy, commonly known as steel, and on the right is titanium alloy. So for the steel skewer, we are going to assume that it's been properly heat treated and that the steel that it's made of is equivalent to that of a property class 8.8 screw. For the titanium skewer, we are going to assume that it's made of grade 5 titanium, otherwise known as Ti6Al4V. So, looking at this first row here, the Young's modulus, also known as the modulus of elasticity, you can see the Young's modulus of the steel is approximately twice that of the titanium. You can kind of think of this as the spring rate of the material. So the titanium stretches almost twice as much when it's subjected to a force. For this second row here, the tensile strength, the yield tensile strength, you can see that the titanium is slightly stronger, and for the ultimate tensile strength, you can see that the grade 5 titanium is also slightly stronger than the steel. Now, if you see the term tensile strength in some specs for a material, that usually refers to the ultimate tensile strength. But the strength that we're interested in is the yield tensile strength. This is the strength where the material becomes permanently deformed. And assuming that you want to use your skewer more than once, you do not want the material of your skewer permanently deformed. Finally, we have the density, and you can see that the density of steel is approximately twice that of the titanium. So the steel skewer is going to be twice as heavy as the titanium skewer, at least the shaft of the skewer. So how much does a steel skewer elongate when it's tightened? We can tackle this question a number of different ways. First, let's go over some basics. So on the road side, road hubs measure 100 millimeters face to face on the front, and rears measure 130 millimeters. So that's basically the distance inside the dropouts on your bike frame. If you go to the DT Swiss website, they say that a conventional quick release exerts a clamping force of less than 4,000 newtons. So for this calculation, let's assume that the clamping force is exactly 4,000 newtons, and we're going to figure out how much the skewer elongates with this force of 4,000 newtons. So the diameter of a skewer is 5 millimeters. So diameter 5 millimeters. So the area of a circle is pi r squared. So that's pi times 5 over 2 squared. So that's 20 millimeters squared. So we need to convert this millimeters squared into meters squared. So to do that, you multiply by 10 to the negative 6th meters squared over millimeters squared. And that gives you 2 times 10 to the minus 5 meters squared. So stress. Stress is equal to force. So that's going to be this force over the cross-sectional area of the object. So that's going to be this area. So force over area. So this 4,000 newtons is 4 times 10 to the third newtons divided by this number here, the 2 times 10 to the minus 5th meters squared. And that gives you 4 divided by 2, 2 times 10 to the 8th pascals. A pascal is equivalent to 1 Newton per meter squared. So 2 times 10 to the 8th pascals. So strain, let's calculate the strain. So the strain is equal to the stress, this which we just calculated, divided by the Young's modulus of the material. Sorry if the table is shaking. So this is the stress here, 2 times 10 to the 8th pascals. And this is the Young's modulus of steel. So looking at our chart here, we can see the Young's modulus of steel is 200 gigapascals. So 200 gigapascals, GPa. So let's simplify this. So this is 2 times 10 to the 8th pascals divided by 2 times 10 to the 11th pascals, because a gigapascal is 1 times 10 to the 9th pascals. So simplifying this, you get 1 times 10 to the minus 3, which is equal to 0.1%. So the skewer elongates by 0.1% when it's subjected to a force of 4,000 newtons. And this is for the steel skewer. So to calculate the elongation in millimeters, we just need to multiply the effective length of the skewer times this strain number here. So the effective length of the skewer is actually longer than these numbers here, because you have some overhang on both sides. There's actually about 30 millimeters that you need to add to that. So if we do the calculation for the rear skewer, taking this 130 millimeters, so that's 130 millimeters, add in 30 millimeters for the overhangs on the end, and multiply that times the 0.1%. And that gives you a result of 0.16 millimeters. So you would expect this steel skewer to elongate by 0.16 millimeters. So not very much. This style of quick release is quite popular. Basically, you have a circular profile around the outside. However, the axis of rotation here has been offset in that direction. And this gives you a camming action as the quick release is closed. So when the quick release is fully open, the initial take up as you go to close it is quite rapid, and as you get closer and closer to the closed position, the take up becomes slower and slower, and that gives you the camming action. So let's do some measurements. First, with the handle fully closed, we're going to call this 0 degrees, and then with the handle at 45 degrees open, and then with the handle fully open. So we want to measure this distance here, and then we're going to zero our calipers, and then we're going to measure this distance here and that distance there. So let's have a go. Okay, so first the 0 degrees, which would be the fully closed position. Okay, 0. And let's double check that. See how close we are. Okay, reasonably close. Okay, let's measure the 45 degree position. So that would be like this. And I get 0.46 millimeters. 0.51. We will call that 0.5 millimeters. And then in the fully open position, so that dimension right there, and we got 0.98 one more time. Oops. Wait, I'm getting confused. Okay, 0.98 again. So actually there's not any ramp with this skewer really, because the amount between here and here is the same as the amount between here and here essentially. On this style of quick release, the axis about which the handle rotates is hidden. Here I've zeroed the calipers with the handle of the quick release at 0 degrees. This is the handle at about 45 degrees. And this is the handle at 90 degrees. So what can we conclude from all this? Well, when I install a wheel on my bike, I tighten the nut down so that I start to get resistance in the handle here at right around 45 degrees. So this part of the stroke is not even used at all, at least in my experience. So when I go to tighten the handle from 45 to 0 degrees, that induces about half a millimeter of travel. However, from our initial calculations, we know that the shaft here only stretches about 0.16 millimeters. So most of the difference between the 0.5 millimeters and the 0.16 millimeters is from movement in other components of the system, such as on the end caps here. Replacing the steel shaft of the skewer with a titanium alloy shaft is only going to double this elongation of 0.16 millimeters to about 0.3 millimeters. So this is well within the capabilities of the quick release handle to handle, even without a redesign. And you could redesign the camming action on this. If you have any experience with titanium quick release skewers, please share below. Also, if you could let us know the brand name, that would be great. Also, if you could subscribe, like, and share, I'd really appreciate it. I'd like to thank you for watching and have a great day. Bye now.